Hi there. I'm Jose Miguel Pacini. I'm a scientist at UTRC, that's the Research Center for United Technologies. I'm doing a master's in data science at WPI, and this video is about some of the assignments I've been working on a data visualization class, which is mostly the concepts of data visualization and then how to embody them by coding them in mostly in D3, but in other tools as well. I'm going to go over the first 3 weeks of work here. So I'm going to go through 1, 2, 3, 4, 5, 6 different visualizations referring to, I'll start with a synthetic data set. Then I'm going to talk about some Comets, then some New York City data, and then some Connecticut race data. So first, I'll talk about a visualization where I just wanted to learn how to do tree maps, where the area refers to the proportion of the total that is taken by something. In this case, I used a synthetic data set. I wanted to use a tree map to illustrate that the geometric series 1 plus 1/2 plus 1/4 plus 1/8, where you're having each additional term, they add up to 2. So this is a 1/2 rectangle. And by illustrating it in this way, it's pretty obvious because whatever is left of once after 1, you are starting to fill in the second square, and you're just adding half of what's left to fill. I added labels here to make it obvious what the sequence was, but for the additional ones, once the rectangles get too small, I also added tooltips so you can actually check that number is 1/2048. For the next 2 visualizations, I'm going to talk about a data set published by NASA, which are the near-Earth comets. So these are comets that pass close enough to Earth, and what it includes are the orbital elements. So these are the parameters of the orbits of these near-Earth comets. So here is a scatter plot matrix of most of these parameters. And we're plotting some variables against others, and we're trying to plot them in all the possible combinations. So we have here E is the eccentricity, so how far from a circle the orbit is. I is the inclination in degrees, so that's how far from the plane of the solar system this is. So 0 would be exactly on the plane. 10 degrees would be a little off, but still orbiting the same direction as all the planets. Over 90 degrees, then they start orbiting backwards. So 180 would be like 0, but exactly in the opposite direction. There are other parameters here. The P is the period in years. Q is the longest, the largest axis of the. So in this case, there are a couple of things that I found striking. The first one was, this was a very nice visualization for this is really Kepler's third law, that the square of the period on orbit is proportional to the cube of the longer axis. So even though this represents over 100 different comets or objects, they all lie exactly on this. So this is perfect, matching perfectly Kepler's third law. So Kepler's third law. I added here color for anything those fragments of the Schwarzmann-Bachmann 3. There's a comet that is disintegrating. I wanted to see where they were lying on it. Now, in terms of visualization, in a scatter plot matrix that is large like this one, it's easy to get a little lost, because I say I'm looking at this one. That means I need to realize that on the y-axis is going to be TP, and on the x-axis is going to be Q. So for that, I added a tooltip. When you hover over the plotting area of that particular element in the matrix, it tells you what are the variables being plotted. Also, if you hover over a specific data point, it enlarges and gives you a tooltip with the name of this comet and the 2 variables being plotted. Now, There's a second visualization that focuses only, I'm going to go back here, only on this specifically. It's a blow up of this one. So this is eccentricity on the x-axis and inclination, so again, how far from the plane of the solar system are on the y-axis. What is interesting here is you see that these dots are kind of concentrated in one area, and then there are others that are all over the place. So it looks like there are two different populations. So this is the blowout of that. So again, eccentricity is on the x-axis. So eccentricity goes from 0 to 1. Eccentricity 0 is a perfect circle. Eccentricity 1 is the ellipse has become so elongated that it's not even closed anymore, it becomes a parabola. So these are very, very elongated orbits. Note that these are very eccentric orbits already, even 0.6. For reference, most of the planets are very close to being circles, even though they're normally plotted as very when one usually sees drawings of the solar system, they look very much like big ellipses. They're very, very close to being circles. So we're talking about 0.07 or things like numbers like that. So way of this scale. So I used color here for a number of reasons. When first I plotted this, I was wondering, what are all these dots that seem to lie on a line? It looked like a mistake. It looked like a noise in the data, or like some kind of an error. So I looked in detail into these, and they all are fragments of one comet. That's why I added the highlighting here. So you can see, even among all the other dots, that these lie on a line. So this was a single object that then fragmented, and now the objects are now they are in different orbits, but the parameters of those orbits kind of have some memory of where they came from. So it would be interesting to see if gonna just try out the math. What happens if, say, you have an object on a certain orbit, and then you then you add noise around it, where you still be fairly on the same plane, but some of them will be a little different. And why would the ones that become more eccentric also be a little farther out of the plane? And so I think there's a whole story here waiting to be discovered. The other thing was that you see most of these are within 30 degrees of the plane, all these gray dots here. And then you start getting dots all over with all kinds of inclinations. So close to the orbit of close to the plane of the solar system, but also very near 90 degrees, and then some that are close to the plane, but orbiting in the wrong direction. Whereas these, you can see that there are no dots on this side. So these are probably, my take on this would be that these are probably comets that were formed out of the material from the solar system itself, kind of breakup of objects. So they are kind of rotating with the group, even though they're now a little off but they're not. They did not flip around, in which case they would have ended up in this area. Whereas these, I wonder if some of these are really objects that have been captured as they pass through the solar system. So then their inclination has no correlation with the plane. The final data set that I wanted to talk about was there are two more. So this one is about it's a data set from New York City Open Data, and it's about collisions and different parameters of collisions. So this includes data from 2012 to the present. I chose 2013 to 2016 because those are full years of data, and I wanted to see specifically what happens with cyclists and pedestrians. And I saw that the fraction of accidents, so these are collisions, what's the fraction of the percentage of collisions that cause injury or death to a cyclist, for example, those are the circles here, and see that 1% up to 4% in July, and then goes back down. So these are numbers that follow what I would call a reasonable seasonal pattern. The collisions affect cyclists more in the warmer weather when there are more cyclists on the road. That's what I expected to see. What I did not expect to see was an inverted trend for pedestrians, and I do not understand it. That more pedestrians there are more collisions that end with injury or death to a pedestrian in winter, and then goes down to summer, where it becomes almost still high but comparable to damage to cyclists, and then goes back up. So I don't know why that is. Maybe it's because it's darker, maybe the roads are slippery, maybe the pedestrians are more distracted because they're all huddled up. So I don't know the story, and I'm very curious to see what could be that. Finally, there's another data set that has to do with road races. So I'm a runner, and I signed up for this Run 169, where you have unlimited time to run 169 races in Connecticut. Why 169? Because Connecticut has 169 towns. And the idea is, I wanted first to give a sense of, okay, how does the number of races that are valid for this Run 169 vary throughout the year. So this is the bar chart here. But I also wanted to see what are the towns, if I want to do every town, there are towns that have few races. So I highlight the towns that have only, according to this schedule, only 1 or 2 races every year. So those are towns where if a race in that town is coming, I may want to run it because there's not going to be another race until a year from now. So in that case, so these are the darker highlights here. I also highlighted automatically the current month and the future months, so that our eyes are focused on the present and the races that are coming. So the idea is that this is a planning tool. Now, this overview wouldn't be very useful, but I wanted to add even more details so that it would be useful to decide what races to run. So here you can see we're in September, we're late September now, and this, when you hover over that, it gives you a tooltip with what are the races from elusive towns in that month. So it gives you the town, just the town and the date. So it gives me a sense of, okay, on this date there's a race in this town. Is this town far or not? I would like to do another visualization where I actually include distance to where I am. The last visualization I want to talk about is an alternative view of this. This is a calendar view of the schedule for the races in 2017. So a calendar view goes all the way from January 1st to December 31st. That's January 1st, 2nd, 3rd. So weeks go down from Sunday, Monday to Saturday, and the months are marked here. Today's date, so I'm filming this on September 28th. There's a red frame around today's date, so the eye can find today's date quickly. And also for every day, I computed the number of races, including repeat races in towns, but also I included, as in the previous case, tooltips showing for that specific day what are the races that are going on. So that again, this gives enough information that I can say, oh, I'm going to run a race in this town, and I know what race it is, and I know how long it is. So the tooltip has the name of the town, the distance, and the name of the race. So a couple of interesting things here is there's a general pattern where we can see that the races are concentrated on Saturdays and Sundays. That there are races during the week as well, during the warmer months, so it's pretty much May to August, which I'm in September, with some exceptions. So here's an interesting exception. There's a story with it. What is this Thursday in November where there are so many races out of nothing? It's Thanksgiving Day. So a number of towns in this, according to the schedule, 11 races. So 11 different races happen on Thanksgiving Day. The biggest one, of course, is the Manchester Road Race with 15,000 people. And other details here you can see is that even when there are races during the week, you don't see many races on Fridays or Mondays. Seems like that's too close to the weekend. Either you want people to recover, or it's so close to the weekend you might as well have the scheduled race for the weekend. So again, these are the ones that I have so far, and I'm very excited as to what's going to come next. I'm still undecided on which data set to focus on, but there are lots of interesting stories here. Thank you very much.